So, in the last few lectures we were looking at solutions for the conservation equation for a unidirectional flow in a Cartesian coordinate system. I had first derived for you the conservation equation for the unsteady transport. Okay. So, for example, partial of C by partial T is equal to d square C by dz square plus any source or sink. Okay. That was for mass conservation. Similar equation for momentum and energy conservation. We had solved these so far for the case where there is no variation in time, so that it is at steady state. Okay. If there is no source, then we saw that an equivalent way to write this is to write this as minus partial j z by partial z plus source is equal to 0. Okay. If there is no source, then the concentration, velocity or temperature is a linear function of position. Okay. If there is a source and that is a constant, I can first evaluate this for the flux. Okay, I can first evaluate this relation for the flux. If the source is a constant, the flux is a linear position, or the stress is a linear position, a linear function of position. And from that, from the constitutive relation, right, for example, that d partial C by partial Z with a negative sign is equal to J. Okay. I can then evaluate what is the concentration field. Okay. So, that is when you have a prescribed source, you can calculate first the flux and then use the constitutive relation to calculate the velocity, the concentration of the velocity. We saw that for a couple of examples. Okay. The first one was for temperature profile, where the source was a constant, it was equal to the viscosity times the strain rate square. Flux was a linear function of position, temperature was a quadratic function of position. Calculate the temperature using the two boundary conditions, and from that you calculate the flux and the correlation, okay, for the Nusselt number correlation for the heat flux. Okay. And then we looked at the flow down an inclined plane. Once again, the stress is a linear function of position because the body force density in this case is a constant. Okay. The body force density in this case is equal to rho g times sine theta, that is a constant. Therefore, the stress has to be a linear function of position. Okay. And if we assume Newton's law for viscosity, we can then find out what is the velocity profile subject to boundary conditions. Okay. Subject to boundary conditions, we can determine the velocity profile, the maximum velocity, the average velocity and so on, and from that we can find out what is the correlation for the Froude number, okay, the ratio of inertia and gravitational acceleration. However, the fact that the stress is a linear function of position can be used even if you have a more complicated constitutive relation, as we saw in the previous lecture. Okay. We examined the flow of a power law fluid down an inclined plane. The relation between the stress and the body force density is the same. Therefore, the solution for the stress is exactly the same as we got for a Newtonian fluid. That solution for the stress does not depend upon the kind of fluid that is being studied. Okay. However, the relation between the stress and the velocity profile is now different. Therefore, I have to use that relationship in order to find out what is the velocity profile. Okay. And we had calculated what was the velocity profile, we had calculated what was the maximum velocity, okay, and the velocity profile, and we had also calculated what was the average velocity. Okay. That required a little bit of algebra here, but it is just integration of powers of z. Okay. So, that the same thing has to be applied again and again, and if you do it without correctly, then you will get an expression for the average velocity as well. So, now we will consider a case where the source or sink does depend upon concentration. Okay. We will consider another case where the source or sink does in fact depend upon concentration. Okay. And that is mass transfer in a fluid film. Okay. Okay, I have a fluid film here, and I have reactant A in the gas phase, and that reactant A enters into the liquid phase, and there it undergoes a reaction. Okay, it undergoes a reaction, therefore, it is consumed in the liquid. Okay. That reactor A is consumed in the liquid. Put a coordinate system here. Okay. This is the z coordinate, this is z is equal to 0, this is z is equal to h, say. So, the interface is at z is equal to h in this particular case, and we will assume it is a first order reaction. So, therefore, the rate of reaction, okay, the rate of consumption of A, okay, is equal to minus K times Ca, okay, where K is the reaction rate constant. So, let me use a capital K, so that is not to confuse with the conductivity, okay. K times Ca, where Ca is the concentration, okay, mass per unit volume. K is a first order rate constant, it has dimensions of inverse time. So, therefore, this reaction rate or rate of consumption of A has dimensions of mass per unit volume per unit time. So, this is a volumetric sink, okay. A mass consumed per unit volume per unit time is the reaction rate. Okay. So, the mass conservation equation for this case, the concentration of A, okay, the mass conservation equation for the concentration of A is just 0 at steady state. We assume that this is at steady state. 0 is equal to d times partial square C by partial Z square, okay, plus the source. Okay. In this case, there is a consumption. Okay, source the reactant A is getting consumed. So, this is equal to minus K times C. Okay. You can verify quite easily that both terms in this equation have dimensions of mass per unit volume per unit time, okay, because diffusivity has dimensions of length square per time. Okay. So, diffusivity times the second derivative, K has dimensions of inverse time. It is a first order rate reaction rate. Okay. This is just equal to dCA by dt, dC by dt. I will just use C for the concentration of A. Okay. So, for notational simplicity, dC by dt is equal to minus K times C, that is the reaction rate. Okay. Therefore, K has dimensions of inverse time. Okay. So, this is the equation that has to be solved, okay, in order to find out what is the variation in concentration with the z coordinate, okay, subject to boundary conditions, okay, subject to boundary conditions. At the top surface, the boundary condition is that, okay, in the liquid C is equal to Cs, the saturation concentration that is in equilibrium with the concentration in the gas. We assume that there is no mass transfer limitation in the gas phase. Therefore, the concentration in the gas is independent of position. That is a good approximation, because diffusion in gases are much higher than that in liquids. For small molecules, the diffusion coefficient in a gas is about 10 power minus 5 meter square per second. In a liquid, it is about 10 power minus 9 meter square per second. So, diffusion in a gas is much faster than diffusion in a liquid, and therefore, I can assume that the concentration in the gas is a constant and examine the variation of the concentration in the liquid. So, the boundary condition is that C is equal to Cs at Z is equal to H, okay, and at the bottom surface, right, bottom surface, we assume that it is an impenetrable surface. There is no flux of mass going across the surface. Therefore, at Z is equal to 0, the flux has to be 0. Okay. At Z is equal to 0, the flux has to be 0, right. That is d times dC by dZ is equal to 0. Okay. And since d is a finite number, it implies that the gradient of the concentration, the spatial variation of the concentration, has to be 0 at the bottom surface. So, this equation has to be solved subject to these two boundary conditions. The solution is quite easy. Okay. You can easily verify that this gives you an exponential solution, a times e power z root of k by d plus b e power minus z root of k by d. This is the solution. In the exponential you have z times root of k by d. Okay, you can get that quite easily by writing this as d square c by dz square is equal to k by d into c. Okay. And this is a linear equation, second order linear equation, and the solutions for these are e power plus or minus z root of k by d. So, this is the solution for the equation where this source, in this particular case this source or sink is now a function of the concentration. So, this is the solution for the concentration field, and now I have to impose the boundary conditions. At z is equal to 0, dc by dz is equal to 0, which implies that a root of k by d e power z root of k by d minus b root of k by d e power minus z root of k by d. This has to be equal to 0, just substituting. And at z is equal to 0, both of these exponentials are both 1. At z is equal to 0, these exponentials are both equal to 1. Therefore, you get a is equal to b. C is equal to a into e power z root of k by d plus and a is determined from the condition that at z is equal to h, c is equal to cs. At z is equal to h, c is equal to cs. So, there is a second condition, and that constant a is determined from this condition quite easily. So, you get cs into e power z root of k by d plus e power minus z root of k by d. You can easily verify that if you substitute z is equal to h in this expression, you will get c is equal to cs. So, this solution for the concentration field satisfies both boundary conditions. Flux is equal to 0 at z is equal to 0. You can take the derivative and verify that the flux is 0 at z is equal to 0, and the value of the concentration is cs at z is equal to h. So, you can just substitute z is equal to h and verify that this concentration is cs. So, that is the solution for the concentration field. Now, in order to find out, for example, the Sherwood number correlation for this particular case, I have to first find out what is the flux entering at z is equal to h. I have to find out what is the flux entering at z is equal to h. The flux is equal to minus d partial c by partial z. It's equal to minus d cs into I have to take the derivative of the numerator with respect to z. I have to take the derivative of the numerator with respect to z. So, I will get root of k by d e power z root of k by d minus root of k by d e power minus z root of k by d. Okay. When you take the derivative of a negative exponential, I will get a minus root of k by d. Okay. The denominator note is a constant. Okay. The denominator note is a constant. Okay. So, is equal to minus d cs root of k by d into e power z root of k by d minus e power minus z root of k by d by e power h root of k by d plus e power minus h root of k by d. Okay. And the flux at the top surface, the total flux at the top surface, Z is equal to h. Okay. It's equal to minus d cs root of k by d. Okay. Into, I just substitute z is equal to h in this expression. Okay. Okay. This is the flux at z is equal to h. Okay. This product here, okay, evident that it is dimensionless. K has dimensions of time inverse, reaction rate, diffusion coefficient, length square per time. Therefore, this is a dimensionless number. Okay. The dimensionless number is actually defined as the square of this. Okay. It is called the Damkohler number. It is the ratio of the reaction rate by diffusion rate. The reaction rate by diffusion rate, as you can, it has to depend upon the reaction rate, the diffusion coefficient, the reaction rate constant, and the characteristic length scale. And from dimensional analysis, you can verify that this is equal to k times h square by d. Okay, it is equal to k times h square by d. Okay. So, therefore, this exponent here, it is equal to the square root of the Damkohler number. Okay. It is equal to the square root of the Damkohler number. Okay. So, therefore, this is, I can write it as minus d cs root of k by d into e power Damkohler number to the half power. Okay. So, it is a square root of a Damkohler number in the exponent, okay, root dA minus e power minus root dA by e power root dA plus e power minus root of the Damkohler number. Okay. So, this is the expression for the flux at z is equal to h at the top surface. That is, it basically tells you how much of A is getting consumed per unit area of the reactor per unit time. Okay. So, that is the meaning of this, the rate of consumption of A per unit area per unit time. The Sherwood number will be defined as the flux by d Cs by h, okay, divided by a quantity which has the same dimension as the flux. From Fick's law of diffusion, d times Cs by h has the same dimensions as the flux, where Cs is the concentration at the surface. Okay. So, this is equal to, if I take the magnitude of the flux, because the Sherwood number has to be defined as positive, flux is negative because it is coming downwards, it is coming in the minus z direction. Okay. That is the reason that you are getting it as negative. Okay. If I take the magnitude of the flux and divide it by d Cs by h, I will get h root of k by d into e power root and this thing once again is the square root of the damn Kohler number. Okay. This thing once again is the square root of the damn Kohler number. Okay. And this is the correlation for the Sherwood number for the diffusion into this film. Okay. This is the correlation for the Sherwood number for the diffusion into this film of thickness h. Okay. And of course, it seems a complicated exponential function. However, we can get approximations for this in the limit where the damn Kohler number is small and in the limit where the damn Kohler number is large. Okay. So, first if you consider the damn Kohler number being small, okay, damn Kohler number is equal to kh square by d, recall. So, the damn Kohler number being small implies that the reaction rate is small compared to the diffusion rate. Okay. The damn Kohler number small implies that the reaction rate is small compared to the diffusion rate. If it is small, I can use the approximation e power root dA is equal to 1 plus root dA. Okay. If the damn Kohler number is small, I can use the approximation that e power root dA is 1 plus root dA and substitute that into this expression. Okay. And in the numerator, I will have 1 plus root dA minus of 1 minus root dA. Okay. So, I will get 2 root dA in the denominator, 2 square root of dA in the numerator. Denominator I just add it twice. So, I will get just a factor of 2. Okay. So, this will be equal to and if you work this out, this just becomes equal to the damn Kohler number. So, for dA much smaller than 1, the Sherwood number is just equal to the damn Kohler number. Okay. So, there is a correlation. And you can consider the opposite limit where dA is large compared to 1. Okay. In the opposite limit where dA is large compared to 1. In this case, the reaction rate is much faster than the diffusion rate, right, because the ratio of reaction rate and diffusion rate. Okay. In this expression, if dA is large compared to 1, that means that the first terms in both of these, okay, are much larger than the second terms. Okay. And therefore, this ratio, because the first term in the numerator and the first term in the denominator, they are both much larger than the second term in the numerator and denominator, because second term is e power minus root dA, inverse of that. You can neglect the second term in comparison to the first term, and the ratio tends to 1, and therefore, you get the Sherwood number is just equal to the damn Kohler number itself. That is the expression for large damn Kohler number. Okay. The Sherwood number is just equal to, I am sorry, damn Kohler number to the half. Okay. Okay. Because the ratio becomes equal to 1, okay. The ratio of the numerator and denominator becomes 1. Therefore, the Sherwood number is just equal to damn Kohler number to the half. Okay. So, these are the limiting cases. For the intermediate case, you have to use this expression to find out what is the Sherwood number and therefore, what is the mass flux in this case. Let us now examine what physically the damn Kohler number means. Okay. What physically the damn Kohler number means. Okay. So, I have this surface here of thickness h, okay, and there is solute that is diffusing and which is getting consumed, okay, and which is getting consumed. Okay. If the rate of consumption is much smaller than the rate of diffusion, right, if the damn Kohler number is small, okay, so that the reaction rate over a thickness h, if the Damkohler number is small, so that the reaction rate over a thickness h is much smaller than the diffusion rate based upon the concentration at the surface. Okay. If the reaction rate is small, consumption is small, right, then I can neglect the consumption term in the conservation equation, and the concentration profile will be nearly a constant, okay, because for that particular concentration Cs, the reaction rate is much smaller than the diffusion rate, and therefore, if the reaction rate is very small, if the reaction rate is 0, the concentration will just be a constant Cs everywhere, because there is a 0 flux condition at this bottom. Material will diffuse in, concentration will increase to Cs, and when it is equal to Cs everywhere, diffusion will stop. Therefore, in the limit of small Damkohler number, the diffusion is dominant and the concentration is nearly a constant throughout the region, throughout the thickness h. The diffusion, the reaction rate is sufficiently slow that the concentration is really nearly a constant, and therefore, the Sherwood number turns out to be proportional to the Damkohler number. On the other hand, if kh square by d is much larger, okay, if kh square by d is much larger than 1, okay, if we take the second limit where the Damkohler number is much larger than 1, okay, in that case what happens? For a given concentration which is comparable to Cs, the diffusion rate is much slower than the reaction rate. So, the material will get consumed by reaction before it diffuses very fast. Okay. The material will get consumed by reaction before it diffuses very fast. Okay. Therefore, the concentration, if you plot it as a function from the free surface, okay, if you plot the concentration as a function from the free surface, it will start off at Cs. Okay. So, this is the concentration, okay, and it will very quickly come down to 0, okay, over a thickness which is much smaller than the height, okay, because the material is getting consumed before it diffuses at distance h. The time required for diffusion over a distance h is going to be equal to h square by d. Okay. So, that is the diffusion time. Diffusion time is equal to h square by d, okay, from dimensional analysis. The reaction time is equal to 1 by k. Okay. So, therefore, if the Damkohler number is small, it means that the diffusion time is much smaller than the reaction time. Okay. If the Damkohler number is small, then the diffusion time is much smaller than the reaction time, right, because Tr by Td is small if the Damkohler number is small. I said it the other way. Td by Tr is small if the Damkohler number is small. So, the Damkohler number can be also expressed as the ratio of a diffusion time divided by a reaction time, okay, where the diffusion time is h square by d just from dimensional analysis. Diffusivity has dimensions of length square per time. Reaction time has dimensions of inverse of the rate constant, because rate constant is 1 over time. If Damkohler number is small, the diffusion time is small compared to the reaction time. Therefore, the material will diffuse over the entire thickness h before it reacts very much, and the concentration will be close to a constant. If reaction time is much smaller than diffusion time, the material will not progress very far, okay, before it reacts. That means that the concentration of the material will decrease to 0 over a distance that is small compared to h, okay, because if the reaction time is much smaller than the diffusion time, Damkohler number is large, okay, the reaction time is much smaller. That means that the material will diffuse over a short distance before it gets consumed, and that short distance is much smaller than the thickness h, okay, and you can estimate what is that distance. Okay. The distance over which will diffuse cannot depend upon h, because the distance is much smaller than h. It can only depend upon k and d, okay, and therefore, the distance to which it will diffuse just from dimensional analysis, okay, is going to be distance of penetration. of the concentration field. Okay. For the case where the Damkohler number is large, so that the reaction time is much smaller. Okay. It can depend only upon K and D, it cannot depend upon H, because H is much smaller than the distance to which it diffuses, and just from dimensional analysis this distance has to be d by k to the half. Okay. So, there will be a thin region here where diffusion takes place. D by k to the half is the thickness of that region in the limit of high Damkohler number, where this thickness is much smaller. This thickness is much smaller than the height h. Material will be confined only to that thickness close to the surface in the limit of high Damkohler number, where the reaction rate is very fast, reaction time is very small compared to diffusion time. So, Damkohler number is small, it diffuses only at a small extent of thickness d by k to the half. Large Damkohler number, I am sorry, in the limit of large Damkohler number, it diffuses only to a very small distance of thickness d by k to the half, because the reaction rate is much smaller than the diffusion rate. Now, the reaction time is much smaller than the diffusion time, or the reaction rate is much faster than the diffusion rate. In the limit Damkohler number small, it will diffuse over the entire region, okay, because it diffuses over a thickness of h before it gets consumed. Okay. And in each of those cases, these are the correlations, okay, dA power half in the limit of high Damkohler number and proportional to the Damkohler number itself. In fact, it is equal to the Damkohler number in the limit of small Damkohler number. And each of these is related to these different pictures. This is where the small penetration depth for Damkohler number being large compared to 1, because the reaction rate is much faster than the diffusion rate. This corresponds to near constant concentration. Okay, this corresponds to near constant concentration, because the reaction the amount that is reacted is small compared to over the thickness h over which the material diffuses. Okay. So, this is an example where the source or sink was dependent on the concentration, okay, and I showed you how to solve this problem in this case. You get exponential functions of a dimensionless parameter called the Damkohler number, ratio of reaction rate to diffusion rate, and you can use that in order to get correlations. Small Damkohler number, reaction rate is small compared to diffusion rate, and therefore, the diffusion occurs across the entire height h before there is very much reaction, near constant concentration. High Damkohler number, reaction rate is large compared to diffusion rate. Therefore, by the time the material will react by the time it diffuses very far. Therefore, the concentration of material is restricted to a thickness close to the surface of dimension square root of d by k. Penetration depth is square root of d by k. Okay. So, these are for steady state with a source that depends upon the field variable. In this case, the source depends upon the concentration. Okay. We will take an example of an electrokinetic flow in the next lecture before we proceed to cases where